Hello, judges and audience. We are the Georgia Tech team for the Ball State University case. This team was done entirely extracurricular through the Energy Club at Georgia Tech. And the team is me, Connor Zinski, Tan Tonj, Saul Haroon, Anthony Doljak, and Jake Churchill. And we also had additional help from Montana Bush from AES, who works in the solar industry, and he helped us by providing some real world pricing for labor and installation costs of these solar panels. So I'll hand this off to Anthony for system design.
I'll be speaking about design of our system. We designed a 7.7 megawatt system with a 2 megawatt hour battery system. The battery's main purpose was really to increase the resiliency of the system. Also, all of this would be tied to the existing grid at Ball State. And we identified 8 buildings for flat roof arrays, a parking garage for a few car canopies, and then also a ground mounted system that is pretty sizable. Yes. So then this slide just kind of gives you a brief overview of all the chosen locations that we had and their designed PV systems. And then also you can see the total kilowatt or total production each month, and also the average production each hour. The first step that we took when designing the system was identifying locations that would be suitable for PV. So some of the things we wanted when we were in a location was that it was unobstructed and free of shading, especially during peak hours, as this is when production would be the greatest. Also, we wanted large areas that allowed orientation towards the sun. And we also wanted it to be allow for reasonably simple installation. We then began making selections on the equipment that we would want. Some of the basic criteria we had was that it had to be UL and IEEE certified. We wanted to be available given reasonable notice. Also, part of our goal was to have a 20-year payback period. So we wanted it to be cost effective and have good warranty and power production guarantees. So ultimately we chose Hanwha's Q-Cell 390 module for our PV. We liked its efficiency rate and temperature coefficients, especially for the kind of variable temperature in Muncie, Indiana. It was also, another plus is it's also manufactured in the US. To decide upon the racking, we first considered the tilt we wanted. For Muncie, Indiana, the optimal tilt would be around 40 degrees. However, this steep of a tilt leads to a much larger inner row spacing, then leading to less aggregate production. This and the limited availability of a flat roof racking system over 15 degrees led to the decision to go with a 15-degree tilt for all our flat roofs. This change from the optimum tilt will only lead to about a 5 to 10% reduction in peak production, so it's really not that much. For the ground-mounted system, we chose a tilt of 30 degrees, as we were not as limited on space, and producing at the peak was more important. Lastly, we chose a variety of Chint inverters. They were chosen to go for about a 1.2 DC to AC ratio. This would allow for some inverter clipping. For the battery system, we chose the Tesla Power Pack 2. We liked it because of Tesla's experience and reliability. I'll pass it off to Tan now to talk about the distribution system impact analysis.
Hello, everyone. So when considering the installation of distributed energy, roll back. When considering the installation of distributed energy resources on this large of a scale, it is very important to consider the effect of adding this PV generation and battery storage onto the existing distribution system. And so to simulate this, I used the OpenDSS solver to model the system with and without the PV generation and battery. So on the right, we see the area under consideration for the competition with the added added generators marked with the blue dots. And since we were not given any details about the service to BSU's facilities planning and management building where the field system would connect, we assumed it was served by a separate feeder or another substation and did not include it in this model, but it would be a necessary step before implementing our solution. And so the generation profiles from Aurora Solar were incorporated into the OpenDSS model, and so they included the variations in solar radiance and shading to determine the generated amount of power for each building's PV system. And then the battery dispatch profile was generated from REOP Lite using the loading profiles provided to us by the competition. And so if we go on to the next slide. So looking at this first plot, we can confirm the reduction in power seen by the meter at the substation when we add the PV generation, and we see the reduction in usage throughout the day as the load increases along with PV generation. And it's important to note that this is a fairly ideal day with a high amount of irradiance during the summer. And so looking at this, so I ran the simulation for a year, solving it every 15 minutes, and as we expected, did not have any overloaded equipment or concerns for reverse power flow through the substation, and circuit voltage levels were slightly improved. And so these two graphs that you see here, they were generated at peak loading times, but so they show those peak loading times, which was the biggest areas of concern. And then, so from this data, I can confidently say that the PV generation will not have any negative impacts on the distribution system, and it will be able to maintain proper operation. And so now I'll hand it off to Jake for the financial analysis.
Hello, everybody. So when looking at a financial perspective for this project, there were two unique considerations. Firstly, the tariff structure from the utility had very competitive pricing at an average cost of 5.25 cents per kilowatt hour, including the demand charge. And so when we optimized our system, we were only able to reach about 5.33 cents per kilowatt hour. So we had to consider the resiliency and the carbon reduction emissions for a comprehensive look at the benefits. And secondly, the rate for consumption was not time dependent. So the battery system was not able to charge during when the electricity is cheaper, and then discharge when it's more expensive to provide value that way. Had to rely on the demand shaving. Secondly, since the field system could not be electrically connected to the rest of the system, we divided the project into a virtual power purchase agreement, which was the field system, and a power purchase agreement. And the VPPA allows the field to sell the electricity directly into the grid. The total construction cost came out to $1.19 per watt, including the batteries and inverters. Not including the batteries, it's about $1.09. And then below here, you can see the VPPA price and PPA price that we settled on. Could go to the next slide. And the reason that we chose these prices is, if you look on the bottom one, we wanted to go as low as possible under the market price for the VPPA, because that system, the field system, produces more electricity than the rest of the system. So that would provide greater revenue for the university. However, to offset that, we had to increase the PPA price so that the investor does not lose money. Next slide. Yeah, so from the university's perspective, a large portion of the value comes from the resilience. And we modeled for about an average of 1 4-hour outage per year. And that you can see the premium that we came up with there. And as we'll talk about later in the strategic alignment section, there's some ways that the system aligns with the goals of Ball State, and that is some other source of value. Moving on to the investor, we reached that net present value of 0 per the competition regulations, and we use a 1.5 debt to equity ratio to finance the project. And to reach that NPV of 0, we had to, or the cash flow is actually negative. But to make up for that, the tax benefits, like the federal ITC and the depreciation, make up all the investor return. So now Connor is going to talk about the development plan.
So for the development plan, for the rooftop and carport application, we looked at these through Aurora Solar, and over the course of a day, there's going to be optimal sunlight on them. There's going to be no shading from the buildings or anything. And for our ground mount system, we looked at several different elements, including the elevation grade, which is in the top left picture. The field's going to be at a constant grade, so other than a few slight modifications, we're not going to need to do any major leveling of the ground surface. And for the soil analysis, soil is primarily clay and silt, so it can just be regular ground mount system. And the zoning and regulation is going to require, since over a 3 kilowatt system, a application will be made for a stage 3 or level 3 Indiana Utility Regulatory Commission application for this interconnection. And for our land use, we needed to obtain these relevant permits and follow regulation. So for the battery and PV installation, we will need to acquire electrical and building permits for Delaware County. And to install these battery and PV systems, we're going to be installing these through NEC 2017 with this rapid shutdown compliance. Indiana doesn't really require this because it goes off of NEC 2008. But however, for the safety of operators and when rapid shutdowns needed, such as for fire emergencies, we determined that it was best to have this system implemented. And for the additional installation, we'll be using 2006 Building and Fire Code as mandated by Indiana. For our timeline, we're aiming for a crew of 10 people to work on each building. When we estimated this house below of around 2 to 7 weeks per building, based on the estimate that it takes about 7 man hours to install one rooftop kilowatt. And that's how we estimated that there for 40-hour work weeks. And a separate crew will do the ground mount system, and based on the cost for a carports, we'll be using a third party for that installation. And now I'll hand it off to Saul.
Hi, everybody. So we saw an opportunity with electric vehicles. We've got a sizable car canopy at this place of almost 0.5 megawatt. So we saw an opportunity to install electric vehicle chargers and even to look at the possibility of V2G, vehicle to grid, for potential research and opportunities there. Next. So we're leveraging a partnership between Advanced Microgrid Solutions and Tesla to help optimize what the system will look like in terms of microgrid control and operation. One of the key things we want to be able to do is ensure there's a clean decoupling from the grid. So such a partnership through an advanced controller system would allow us to, both on the medium voltage side, but also on the low voltage side, to be able to decouple cleanly and also identify critical loads and then feed the microgrid in standalone mode to critical load panels and critical load switchboards as well. We also want to be able to explore DC-based subsystems for DC microgrid for perhaps even better efficiency. We want to look at energy management. We want to make everything visible to everybody. So to that end, we are going to be working on creating an educational STEM program to inspire the next generation of engineers. Next. So our optimization strategy basically is in line with Ball State's district master plan of 2015, which entails that all new buildings be pretty much net positive or LEED certified at least. And the Architecture 2030 challenge is also in line with that, which requires net zero energy compliance by 2030. So Ball State's own master plan basically indicates an energy offset around 9% if all the building surfaces feature solar arrays. Our calculations with our very sizable ground mount system is coming in around 18% of meeting the 50,000 megawatt hours of energy consumption per year. So we feel we're very much in line, and with intelligence, with data analytics and AI, and a really clean partnership, Advanced Microsystems and Tesla, we feel we can create a microgrid that will really address all these demands in a clean way. So thank you so much. And we'd like to thank our sponsors, the Energy Club, which include Georgia Power and Georgia Tech's own Strategic Energy Institute. At this point, we open it up for questions. Thank you so much.